we are going to study about everything about the spectroscopy and analysis of organic molecule structural identification. 이거 내도 문제 아니야? 처음 보는 거야? Everything else is a spectroscopy, but mass is a spectrometry, not spectroscopy. 뭐가 다른 거지? 동훈아, what's the difference? Why mass is not spectrometry, not spectroscopy? 그거 봐, 내 이름도 모르는데 알겠어요? 어? 신유. 대원이. 수가 홍주. 이야, 이거 충격인데? 오케이, 내려. Okay, IR spectroscopy is absorption spectroscopy, not emission. NMR is emission, and NMR is for nuclear spin. Electronic transition is for UV visible, and vibrational mode is for the IR spectroscopy. PC로 연습해봐. 벌써? 왜 이러지? 간단한데? 조기님 다시 줘. 바리스라도 먹었나? 왜 PC가 자꾸 쓰지? Okay, IR spectroscopy is for vibration, and if you think about the vibration in organic molecule, those vibration can be carbon-carbon vibration, carbon-hydrogen vibration. They are main source of a vibration, right? So, what is the unit of IR? Wave number is in the unit? Nanometer? Centimeter? Millimeter? Centimeter? To the minus 1 over centimeter, right? So that's 1 over centimeter. So this is wave number, but this unit is 1 over centimeter. So this is frequency unit. And frequency unit was about 500 to 4000 range. So this is the usual the IR range. And among this IR, then if you look at those the IR, it's an absorption spectroscopy. So you have two ways. One way is you have a light input here, and your sample is here, you detect behind. So you can measure transmitted light after absorption. So you can measure either absorption amount or transmission amount. If there is absorption happens, then you can do maybe observe this amount. So this is one way you can show. Or you can measure it is actually you detect the light. So measuring is actually transmitted light, right? So in IR you have two ways to show the y-axis wise. This is absorption, this is a transmission. So usually currently we use absorption like this. So this is 100% here, and this is 100% of the transmitted, and this much is absorbed light. Okay. So if it's a strong absorption, then it can go maximum up to here. This is 100% absorption. Okay. Go to Kahoot. So in IR, we are measuring those CH vibration or CO vibration, CN vibration, C halogen vibration, kind of different kind of vibration we measure. So most abundant vibration will be CH, right? There are many CH. So CH is a dominant here. Then among CH, we cannot distinguish many things. So that's why we can see something special in there, special vibration, like OH, NH, which has hydrogen bonding. That vibration has unique band, and another band is for, okay, 한번 더 하자. CO double bond has a unique bond. 이번에 오메가를 받아보자. 빨리 들어. 자, 두 번째 푸니까 이제는 첫 문제는 다 맞춰야겠지.
참가 안 되는데.
어?
참가 안 되는데.
왜 안 됐어? 빨리 불어. 밑에 번호 있잖아. 2627906. 두 명 못 들어왔네, 한 명 못 들어왔네. 이제 들어왔어, 지금이?
아직
됐니? 오케이. 그래도 틀려. 누구야, 누클리어 스핀? 누가 이렇게 의지가 막강해? 야, 또 동훈이야?
네.
CH vibration is here. 3000. Majority of them is here. There are many CH. So if you look at the IR spectrum, majority of CH is here. This is clean, and there is a lot of peaks here. This area is almost impossible to predict. So this area they call this fingerprint area. If you look at this area, then you can guess what is the molecule. Okay. So among those spectrum, which one we are going to look at is the IR. So CH is a little less than 3000. If you can make a hydrogen bonding sometimes depending on the concentration, it can be stronger, weaker. It's a mixture of exchanging. So that means it can be broad peak, and it shows around here. So if you see broad peak here, then there is either OH or NH. Okay? Other than that, you see this peak, this area is clean. Okay? That's IR. CO double bond. Okay, if there is any carbonyl group there, then there will be very strong peak, sharp peak around 1700. This is kind of the unique peak in IR. So there are many functional groups we have learned. Chloride, OH group, OH group is here. There are many CH is almost impossible, it will overlap here. And CO bond is difficult to see, but CO double bond very strong peak, almost 100% absorption near 1700. And this is reciprocal centimeter. So this 4000 compared to 500, the energy is higher or lower? It's higher because this is frequency. Okay, this is a higher energy here. Okay, so this is main thing usually we look at from IR. So century ago, IR was a powerful technique, but it can give very limited information. Now go to the NMR. Okay, NMR is a ppm unit we use. In NMR, we have a 0 ppm to 10 ppm range as a reference. And you need to determine which side is upfield, which side is downfield. And 0 side is upfield, 10 is downfield. And going to the downfield, electron density around the hydrogen is lower or higher? 하나만 답변해줘. 유민아. In 10 ppm range, electron density around the proton is higher or lower? 10 ppm, 0 ppm, 10 ppm. 0 ppm is upfield, 10 ppm is downfield. Downfield is more, electron density is high. Lower, yes, very good. Okay, so here, NMR is measuring those spin, the magnetic, the energy level. Right? By applying strong magnetic field, this magnet is aligned this way and this way, and that is divided into like this. But that energy gap is very small, near to the microwave. And among those range, if hydrogen has more electron around, these electrons are shielded. Shield means cover from external magnetic waves. So they protect, they resist. That's why the magnetic effect becomes smaller. That is why it goes to 0 ppm direction. Now go to the NMR. So here is a 0. This is a 10 ppm. So this area, as we put, electron density is higher. Now if you look at those, if you have an electronegative atom near to carbon, they attract electron, right? That is the de-shielded. If there's electropositive one, silicon. All others, carbon, N, or oxygen, or halide, if you have those kind of things, they move from here to these directions. I said that this is ppm is energy difference between this one and this one. And out of here, 100만 분의 1 to 100만 분의 10. This range we are looking at. So the energy gap is very small. That's why we need to have a reference. Usually we use this one as reference. TMS. This is the TMS. Because of this electropositive one, electron is more moved to this direction, so they have a lot of electron density, and use the TMS as a reference of 0, internal reference. Okay, so this is typical upfield reference. Make sense? Now, if we have one heteroatom, approximately it moves to around 3. If you have a 2, you have around 5, 6. 3, like a chloroform, then it moves the further. Simple IQ is near to here. Silicon is a 0. Simple IQ is around 1. Here. There's the simple IQs. Okay? Now if we have heteroatom like a chloro, heteroatom attract electron, de-shield, remove electron, and they move to downfield. How much? 그래서 막 답을 적어줘. Around the 3 ppm they move. Okay? And if it's oxygen, not halogen. Heteroatom, what we have learned so far, nitrogen, oxygen, halide. They are electronegative atom. And all together approximately 3, easy to remember. Right? Heteroatom, one heteroatom is shift goes into around the 3, originally around the 1. Okay? Next to carbonate. Alpha position of carbonate. This position. Now you can think electron withdrawing power of carbonate is stronger or electronegative atom is stronger. Carbonyl has electron withdrawing effect like this, but that effect is not stronger than heteroatom. Okay, so that's a little weaker. So just a simple CH around 1, heteroatom around the 3, and alpha position of a carbonyl about to 2. Aromatic ring. Benzene, toluene, phenol. If the hydrogen is attached to aromatic ring, there is some explanation of ring current. So that you will learn in the next semester. But anyway, aromatic ring about 7. How about benzylic position? This position. That position is also similar to carbonyl's alpha position, about 2. Okay, let's just summarize. Without any heteroatoms or functional groups, if a simple alkyl group around 1, very upfield 1, reference silane, silane compound is a 0, and all others is about 1. If you have any heteroatom, oxygen, nitrogen, halogen, then they move to around 3. If you have 2, they move to double. 3, maybe triple, a little less. If there is any carbonyl position or benzylic position around 2. Aromatic ring around 7. 거의 다 보였어. 속성 학원 강사다 그지? 그게 겹치면 benzylic position and heteroatom. If it's a double effect, two plus 3, about 5. Now makes sense. The shielding effect, one is by the electronegative atom, the other one is by carbonyl or benzylic position, then it has kind of an additive effect, approximately. Okay, let's check one by one. Trimethylamine, approximately. How many heteroatom there? trimethylamine. How many heteroatom there? 1. Then that trimethylamine, amine here, CH3, CH3, CH3. So next to this carbon, there's only one heteroatom, about 3. Okay. Chlorochrome, they have a 3 chloro. Then almost maybe near to 9, but that's not exactly triple. That's a 7 point something. That's accumulating. If you have a 2 heteroatom, approximately maybe 5 point something. 두개보다 조금 작게. Okay. So that's the general trend. Heteroatom 3, carbonyl and benzylic position 2. If you have both of them, you can add and a little less. Aromatic ring about the 7. Exception is aldehyde. Aldehyde position, this position. There is also similar explanation of ring current. Aldehyde is about 9. Carboxylate is even going over around 10 or even 12, a little off. This carboxylate effect is done by hydrogen bonding. If it is a strong hydrogen bonding, then this electron density around is higher or lower. If that hydrogen proton is involved in hydrogen bonding, electron density around that proton is higher or lower? Lower, because 2 heteroatom is attached to that and extract those electrons. That's why it's moving to the further and further downfield. So they can move around between 10 to 12 range depending on those solvent environment. Solvent is strongly polar, then they move down further. If it's organic solvent, they move out a little. But anyway, that's the exception. Around 9, above 10. So this is all about the proton NMR, approximate table for chemical shift. Okay. In NMR, when you study, chemical shift is one information, but there is another information, coupling. In NMR, this is attached to this carbon, next carbon, and these 3 protons, they act as a small magnet each, and then they interact each other. If there is only 1, then that divides this peak into 2. If it's a 2, and it becomes a 3. If it's a 3 like this, then it becomes this one, make into 4 peaks. That's the so-called coupling. That also gives a lot of information. If you look at those coupling pattern, then how many proton is in the next carbon? Is the information of we can get. That's the coupling pattern and coupling constant. This is a 4. How about this? This is the question. If this is a 4, and this one, how many peaks do you expect? Singlet, doublet, triplet, quartet. It's a doublet because it has only 1 proton is here. Okay. So if you look at those information, you can see the quartet and doublet peak here. 누가 컴퓨터에 바이러스를 심었어요? 나는 문제는 뭐였더라? 애니멀 스페로이드는 또 뭐가 돼 있지? Okay, this is kind of quick summary of IR and NMR, and they utilized electromagnetic wave in IR case, they use the IR range of light, right? And in NMR, which range of light they use? Radio wave or magnetic microwave range of that energy. So visible light here, shorter than visible light, you have UV, X-ray, gamma ray range. And if it's getting longer, and visible, IR, and microwave, and radio wave. For some time, we didn't look up this in between IR and microwave. This range of light is called the terahertz, the light. Because we didn't have that, the light source, we didn't study this very well. Recently coming up to show, to see picture. So that kind of range, depending on the electromagnetic wave, the frequency, we can get different information. So this kind of the information, interaction of the material and light, if you have this kind of interaction for study, then we call this as a spectroscopy. Why spectroscopy? Because it has a spectrum. It has been used, okay. See which one. Now we didn't study the carbon NMR, the strongly, but let's say carbon also has a similar pattern like this, but it has a little bigger scale, 0 to 200 ppm range of the carbon spectrum. And then in carbon case, it has a very sharp peak, even sharper than proton. So if you look at this molecule, benzene, how many carbon signals do you expect? How many different carbon here? Only one, right? Or 6 carbon is equivalent. So they show only one peak sharp. If you have a phenol, how many carbon signals here? Two. Let's count. 1, this is a different. 2, this 2 is equivalent. This one is also different. The distance from oxygen is different, right? This one is also different. Actually, we expect 4 carbon signals. We can expect. Okay, make sense? If I have this molecule, how many carbon signals do you expect? 2. 1, 2. This 2 is the same, this 2 is the same. If I change this, how many signals do you expect? It's a 4. This one and this one in proton and NMR, they have a similar effect, but they are not identical. Okay? If they are not identical, we can see different peaks. And if you look at this molecule in proton and NMR, how many proton signals do you expect? 1, that's also proton, and then 2, this is identical, and 3. 3 peaks you can expect. Okay, so this is very basic of NMR. So mass spectrometry, from mass spectrometry, we can get molecular weight. And long time ago, if you have a molecular weight, then there is a fragmented pattern. Then by looking at those molecules, how this molecule is fragmented to generate this daughter peak. This is a mother peak, and this is a daughter peak. And then we could guess the connection of these molecules. That's a last century chemistry. 분석기기가 많지 않았을 때는 그것도 굉장히 소중한 정보였기 때문에 그걸 들여다보면서 메틸 그룹이 들어있었구나. 뭐 이런 거를 저걸 보고 스타디를 했다는 거죠. 머리도 좋아야 되고, 눈도 좋아야 되고, 분석도 좋아야 됐을 거예요. Now we have a much better machines and much better analysis technique. So usually we don't look up fragmentations. Usually we see molecular weight. Now if you look at those molecular weight in ChemDraw, and there are 2 molecular weight there. There is molecular weight and exact mass. 2 values they give. How are they different? And here, this number you see here, is that molecular weight or the exact mass? What do you think?
뭔가 아닌 것 같은데.
Molecular weight is the average atomic weight for coming up of all the isotopes. We have isotopes of the carbon 12, carbon 13, carbon 14, and they are evenly distributed. Not the same ratio, but they are distributed. So if you look at those mass, they measure those isotopes as a separate peak. So that's why if you calculate yield and average yield, then you need to use molecular weight because that's a mixture. But if you look at those data in mass spec, those data is showing you the exact mass. And different isotope will show up as a separate peak because they behave differently. Make sense? So that effect we can see very strongly if you have a chloride. In chloride, you see mother peak is 64, and there is about 1/4 size of M+2. Why is it? Chlorine has isotope of chlorine 35 and chloro 77. Three to 1 ratio, and that ratio is reflected here. So if you look at M+2, about 1/3 the size of original peak, there may be chloride in this molecule. That's the information you can get. Okay. So in mass spec, you can see usually molecular weight, so the size of the molecule, and little extra information. If you look at your mother peak M+2, as in chloride, but not 3 to 1 ratio, if it's almost 1 to 1, what's that? That's a bromine. Bromine has a bromine 79, bromine 81, they have almost the same weight. 79, 81, exact mass is different. Average mass or molecular weight is in the middle, 80, because that's average. Make sense? So that's molecular weight and exact mass difference. So from mass spec, we can get this kind of information. Okay, if you look at spectroscopy, as we said, we have a different kind of wavelengths of electromagnetic wave. And these all different kind of light all together as a bundle we call spectrum. Spectrum from long wavelengths to short wavelengths. If you use this spectrum for study of a material, that science is called as a spectroscopy. So that means in the interaction study, if there is light has been used, any wavelengths among these, X-ray spectroscopy, gamma ray spectroscopy, visible UV spectroscopy, IR spectroscopy. NMR, they use this range spectroscopy. In mass spec, there is no light source. All you need is magnetic field. You didn't use light. That's why it is not called as a spectroscopy. But it is measuring, so spectrometry. Okay. So for those spectroscopy, we didn't learn this, but this one is the first chapter of the next semester. UV visible spectroscopy. They measure electron in transition. This energy gap is UV visible range, which generates the color to our eyes. Okay. So in this chapter, we learn IR spectroscopy, which reflects those information of molecular, the molecules, the vibration or rotation. Okay. And as I summarized quickly, from 500 to 400, the higher level here, this is the transmittance. If it goes down, this is the absorption. Okay, measuring is the transmittance this way, and then this is the absorption is going down. Now, majority of those molecules, if it's organic molecule, CH bond is about around here, a little less than 3000 range. Sharp, and then a little less range here. Depending on those molecules, sometimes this is simple, sometimes complicated. So this is a fingerprint range, less than 1000 range. That part is difficult to assign. Typically, this shows that, oh, this is an organic molecule. It has a CH bond. Okay? If it's inorganic molecule, you may not see these bits. Now, among this, so big table of IR, but the most important thing here is CH bond a little less than 3000. That tells this molecule is organic molecule. Another important peak is a broad peak above 3000. Hydrogen bonding, OH vibration. That's uniquely you can see. Another very strong one is CO double bond. CO double bond stretching is very strong, and then it is a little bigger, a little lower among those the double bond, the ketone, aldehyde, ester, amide. They are slightly changed, but around the 100, the 1700 range. So, example of, if you look at this kind of IR spectrum, oh, there is OH, or there is water. Sample 물이 먹었군. This is a signal of hydrogen bond. Okay. Hydroxyl or water contamination. And if you look at, so this is ethanol. And if you look at this kind of signal, very unique one is here. 1700, very strong peak here. This is the signal of carbonyl group is there, CO double bond is there. This molecule structure is like this, aldehyde. So even though there is a big table in IR, other informations you need to look up those original table and compare very carefully. Then maybe you can see, or you may miss your peak. But these are two. This and this, you should not miss. That tells you that, oh, this molecule has a carbonyl group in there. This molecule has an OH group in there. So IR gives you some partial information about the functional group by utilizing their vibrations. The information, as you can see, is relatively limited. Now, that's why NMR becomes very important. NMR, nuclear magnetic resonance, or normal research, NMR tells you everything. And let's see. So this is a table of NMR. Chemical shift between 0 to 10. Okay. Usually those peaks, if there is nothing around, means no heteroatom around. If it is simple hydrocarbon, around 1 ppm. Okay, that's a base. Reference to TMS, silicon compound 0. And then if you have any kind of heteroatom, oxygen, halogen, around 3 plus. Okay, around 3 ppm. Carbonyl, next to carbonyl positions, about 2. Electron withdrawing effect comparing to heteroatom to carbonyl, this is a little stronger. That's around 3. And carbonyl about 2. And I also said benzene position is also around 2. So this 2 is around 2. Heteroatom about 3. And similar, so halogen, oxygen around 3. And aryl group around 7. Phenyl group next to the aromatic ring around 7. And aldehyde exceptionally a little longer, around 9. Carboxyl acid around above 10. So this is a general guideline. Okay, 이것만 갖고 잘 모르겠지. Using this, now here is your molecule. If you take NMR, then let's check whether you can analyze your molecule. So if you look at this molecule, now you can guess how many protons are there. This is a proton NMR that gives you information about the proton. Carbon NMR, you look at totally different window. This is a proton window. As we said, those energy gap here, we are looking only this small area, very small window. and extended that into 0 to 10 ppm. So that's why NMR window, carbon window, and other nucleus windows are totally different. We need to look at that area specifically. And they are shifting around. That's why we need to have this kind of reference inside. TMS we put 0, and then if you look at this molecule, this carbon is connected to carbon. There is no heteroatom. And then CH3, 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 this methyl group, all identical. So they give you the same signal. Because this is rotating here, then you cannot distinguish these three. Then it gives you around the 1 ppm peak. And very interesting in NMR, proton NMR, the integration, this area of this peak looks like sharp peak, but if you look closely, they look like this. Then you can integrate this area. That integration is showing like this. That integration is usually proportional to proton number. So that's very useful information too. Then, now if you don't know your compound structure, then you can give relative area. Okay? So then, if you look at this molecule, here this is a 9 proton, here this is 3 proton. If you take the NMR spectrum, it may give you the ratio of 3 to 1. Then, by getting your molecular weight from mass spec, then you can guess approximately how big is your molecule. Then you can assign these peaks. Now let's see. So here, 9 peak sharp singular. And here, this is CH3 next to heteroatom. Heteroatom about 3 point something. So 1 peak here, 3, and this one is a 9. Another peak is around 1. I gave you very brief the indication. 1, 2, 3, 7, 9, 11. They can be slightly shifting, but approximate range you can guess where you can see. Okay, very simple molecule here. How about this? Ethyl group. One of those simplest molecule we can see. Ethyl group. Now CH3, CH2. Now they couple to each other. Next to this carbon, there is another protons. So this is CH3. Let's look at first. CH3, next position is the carbon. That's why they should show up around the 1 point something. Okay? And this is CH2. It's next to heteroatom. It should come around the 3 point something. And coupling constant, coupling pattern. This one, next to this, they have a 2. Then it should show triplet. This one, next to this, it has 3, then it should show quartet. So now, ethyl group's signature is quartet and triplet. If you see these two together, oh, there may be ethyl group here. And those ethyl group, what is connected to this CH2? Oh, it's a 3 point something. There may be heteroatom here. If it is around 2, what's your guess? Either benzylic position or alpha position of a carbon. That's your guess. Okay. If you look at this molecule, there is no further proton. So that's why that's it. 3 proton, 2 proton. Finished. 1.51. If you multiply, this is 3, 2. So that's an area. This is a chemical shift position of the molecules. Now those are coupling. If there is a 1 proton next to each other, then they interact with this proton. So this is signal is one interaction with this, the other interaction with this. It becomes 1 peak, becomes 2 peak, like this. But if it has 2 proton nearby, then it divides into 3. So 2. If it has 3 nearby, then this interaction is 4 times. So it shows 4 peaks. And this interaction is the same to each other. So this interaction to this interaction, the size is the same. That's why this coupling constant, and this coupling constant, it should be same, identical. It's a mutual interaction. That's why pattern-wise this is triplet, and pattern-wise a quartet. This number of the peaks tells how many protons nearby. And the size of this coupling constant, usually we give that the unit as a hertz. And that should be identical. As this is identical, if there's a multiple coupling, then you can find out which one is a coupling with which. You find out that you get the same coupling constant, the peaks. Okay, let's look up for the example. This molecule. Let's look at this is CH3, CH3. Symmetric, identical. Right? Identical, 6 peak we expect. And then how many neighboring proton? 1. Then you expect doublet. Doublet coming up here. Chemical shift, its connection is to carbon, no heteroatom, 1 point something. Middle proton here is attached to heteroatom, 3 point something, or a little bigger in this case, 4. Now, look at those neighboring group. How many proton in the neighboring group? Totally 6. Right? Then coupling of this is 7, septet. Those are coupling numbers. If there's nothing nearby, it's a singlet. If there's 1 proton nearby, doublet. 2 proton nearby, triplet. 3 proton, quartet. 4 proton is quintet. 6 septet, it's a 7. Why not the 5 here? 5 and then sextet, 6 peaks. If you think about 5 equivalent, it's difficult to think, isn't it? If it's attached to 2, then 2 by 2, this quintet. 3 by 3, maybe septet. The 5 identical one is a little difficult to think, right? That's why usually you don't see sextet. So either quartet, quintet, septet. If it's more than septet, what do you call? Multiplet. It's difficult to recognize those. Okay, example. Now this molecule. With this molecule, now we can see, okay, here, ethyl group. Ethyl group, then we expect triplet and quartet, and chemical shift. And the position around 1 point something. And this one is connected to carbonyl. Carbonyl is a ppm wise about 2 point something. Near to 3, but 2 point something. So this is 1 ethyl here. Now this methyl group, there is no nearby other proton, so it's a singlet. And position next to oxygen, 3 point something, singlet. Now there is something else on the aromatic ring. This the proton identical. This the proton identical. Around the 7, and they shows up 2 peak like this. Now in this case, this proton interact with this. This proton interact with this. Double. So in this case, symmetric through this axis. So this one and this one, double and double. Coupling constant of those, this coupling constant should be identical. So if you look at W over W, then you can expect here, maybe that's a para position substitute, and shows this thing. If it's not para, it's a little more complicated. If it's a single substitute, toluene. CH3 is a benzylic position. Benzylic position around the 2. And there is no neighboring proton, that's why it's a singlet. And now here, how many different kinds of proton do you expect? You know? How many different kinds of proton do you expect? 3. 1, 2, 3. Now those 3, if you look at this 2 has a 1 neighboring hot proton, so this should be doublet. This one is also, this one is 1 here, it should be triplet. This one 1 here, doublet over doublet. So it's more complicated. That's why, and result-wise, this is 2 proton here, and this is 3 proton here. There is a doublet here, and another doublet here. There's an overlap together. So that's why this thing, all together you can say it's 5 proton around here. The pattern is a little more difficult to look at than this one. Para is the simplest. Doublet over doublet. Okay. Now let's look at carbon. Proton between 0 to 10 ppm range. Carbon has a little different window, and 0 to 200 window. Similar rules. If you have electron withdrawing group, then it goes to downfield. Okay. In proton, if you have nothing nearby, it's connected directly to carbon, it is around 1. Now this one has a little bigger range, so it has usually around 10. If you have heteroatom, it goes to 30, 40 downfield shift. 2 heteroatom, maybe double. We are talking about the carbon now. Now, if it is aromatic ring, like a benzene ring, then they are around 120, 130 range, around here. And one more unique thing is carbon and CO. CO is around 200. That's it. If you have nothing, around 10. If you have 1 heteroatom, then about 15. If you have aromatic, 120, 130. 200 carbon. Practice. Now if you look at this molecule, methyl, ethyl, ketone. So let's look at here. This one next to carbonate, so a little weaker. So up the heteroatom is about 40, 50. So this one is a little weaker, about 30. End of here, CH3, this one has connected to carbon, that's around 10. Again, TMS is referenced here. TMS again. This molecule is also referenced carbon, 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 electropositive. That's as reference as 0. Now here, C1 carbon here, C2 carbon, C3 carbon here. This one is connected to carbonyl. That's why it's a little higher. And then carbonyl position is around 20. Now if you have aromatic ring, this shows up around here, 120, 130 range. Carbonyl 200, and this methyl group around here. Now proton, the integration reflects very nicely of those proton number. Carbon not always. Carbon signal is depending on other environment. If it has hydrogen, it has a little slightly bigger. If there's no hydrogen, that's a little smaller. That's why carbon is usually smaller. So integration does not work in carbon. But combining these together, we can guess your molecule structure. So let's look at this. Ethyl group. So this ethyl, this methyl CH3 may be around 10. This one connected to heteroatom around 56. And carbonyl group, how many carbon do you expect? The aromatic ring. Here, how many do you expect? 1, 2, 3, 4. Right? So 4 fit here. Around the 200, you have carbon. So this is general one. Now, if it goes a little further, if I give you information of a molecular weight, and then gives you proton NMR, and other spectroscopic data. Based on that information, you need to build your molecule structure. That's a real structural identification. So if you have molecular weight, first thing you need to do is the calculating degree of unsaturation. Do you remember the formula of that? So this is the formula. If you have a carbon number, then 2n plus 2, that's the maximum hydrogen number. Right? And subtract hydrogen number, and then divide by 2, then you can get the double bond number. Double bond or ring. Right? And halogen is similar to hydrogen. Nitrogen is the opposite, that's why nitrogen case is a plus. How about oxygen? Oxygen, no effect. Even though there is oxygen or not, this degree of unsaturation does not change. Okay? Now, based on this, now if this is your problem, molecular formula and NMR, figure out your molecule structure. 누가 해볼래? Okay, if you look at those NMR spectrum, first of all, degree of unsaturation. How many degree of unsaturation there? Double bond number, degree of unsaturation. 0. 4 multiplied by 2, 8 plus 2, 10, 10 minus 10, 0. So there is no double bond, no ring. Okay, and signature of this. What is there? This. Don't know what's there. It's ethyl group. Ethyl is here. CH3, CH2. That's signature of an ethyl group. This peak is a quartet. This peak is a triplet. That's signature of ethyl group. And how many total carbon? 4 carbon. Seems like there's only one ethyl. That means this molecule is symmetric. And which side there's oxygen? If you look at these two peaks, which one is connected to oxygen? Which one is connected to oxygen? This is connected to oxygen. Chemical shift is around 3. Now, not many options. What is the molecule structure? 지우나? What is the molecular structure? Tetra, T-butyl, alcohol, 지우나? What is the molecular structure of that? 왜 갑자기 다 나무 눈을 안 맞추려고 그러지? 유빈이만 눈 맞추고 있나? 항상 그래. We don't have another group, only simply there's only ethyl. That's why tetrabutyl does not make sense. Only ethyl, and you have a totally 4 carbon. And it implies it's symmetric. And CH2 is connected to oxygen, diethylism. This is the only option. So if you suggest this molecule, this is your model. After you make your model, sometimes you should check whether this model makes sense or not. And if you look at here, okay, CH3 group here, 1 point something, makes sense. CH2 approximately 3 point something, next to heteroatom, makes sense. Okay, that's a reasonable model. But time to time, there is almost possible other options too, sometimes. Then you need to figure out exactly what's the structure. That's the problem. This is one of those simplest problem. Okay, how about this? So we can use the information here too, relative area. Now if you look at the total number of a proton, then you can guess that area means how many proton each. So based on this information, 누가 나와서 모델을 만들어 볼래? Is there a double bond? No double bond. Degree 1 situation 0. Okay, that should be done first. Okay, there's no double bond, no ring. And you start with the simple one first. Simple one seems like the basic one has a 6 proton and it has 1 proton into the next position. That's why this is a doublet. Okay, then you can start with a fragment first. Okay, I have seems like identical CH3 and next position has a 1 proton. And seems like there is symmetric structure. Maybe I can assume this kind of a structure. Okay. And next one, there is a bromide, halogen, heteroatom. Seems like this is connected to that heteroatom. And that one is how many proton? 2 proton. And next to it, also 1 proton is next to it. 조각조각을 만들어서 최종 카본 4개짜리 분자를 만들면 되겠지. 누가 해볼래? 크게 써줘야 대분하게. 하이드로전이 작다고 또 하이드로전 작게 그리네. 카본보다. 왜 이 카본은 이렇게 크고 이 카본은 이렇게 작대? 왜 이 카본은 이렇게 얘보다 더 작아?
좁아가지고.
오케이. 자, 종이 그린 구조를 보자. 구조를 보면 이만큼 먼저 구조를 만들었으면 나머지를 어디다 메우면 될까? 화분이 지금 하나밖에 안 남았잖아. 화분 하나 뽑아내고 이렇게 붙이면 대충 맞나? 같은 그림이야. 이렇게 이제 비교를 해봐. 이게 맞게 된 건가? 요거 두 개, 6 proton and doublet. This one, 2 proton and doublet. Next to heteroatom. 그렇듯하네. This one, now this guy has a 6 here, 2 here. 6 gives 7, and this gives 3, so this will give total 21. Maybe overlapped and then smeared out. Maximum number you can expect is a 21 peak and 1 proton. And all carbons, so that's why this one is also a little high, but that's not very high. 1.9 or something. 오케이. 야, 한 번에 다 하긴 어렵다. 여기까지 하자. So now we have one class next week. So we are going to continue this structural analysis. 자, 본 것처럼 제법 연습이 많이 필요할 것 같지. 그런데 이거 잘하면 중교학을 대단히 잘하는 거가 되는 거야. 그걸 보면서 스펙트럼을 분석할 수 있는 거니까. 내가 지난번 숙제 줬을 때 챕터 13에 앞쪽 부분만 숙제로 줬어. 뒤쪽 부분에 보면 응용 문제가 이런 종류의 응용 문제가 훨씬 더 많아. 내가 뭐라고 숙제로 주진 않을 테니까 알아서들 공부해와서 다음 시간에 같이 연습할 때 풀 수 있도록 준비를 해주겠습니다. 다음 시간에 한 절반 정도는 교재 분석 한 절반 정도 같이 하고 남은 절반은 지금까지 중간고사 이후에 배웠던 단원들 한번 풀어보는 거고 다음 주 마지막 수업을 보고요. 그리고 다음 주 목요일 날 수업 시간이 시험 볼 거고 그런데 생화학 수업이면 두 사람 조금 늦게 온다고 그러니까 시험을 11시 10분에 시작할까? 그랬을 때 문제 있는 사람? 그럼 시험을 11시 10분에 시작한다. 다음 주 목요일 날 기말고사를. 그리고 시험 보는 날은 배부르면 안 되니까 내가 다음 마지막 수업 끝나고 나서 피자 사줄 테니까 피자 어디게 제일 맛있냐? 조교님 도미노 걸로 주문해 주세요. 수업 끝날 때 피자 배달 오면 피자 파티 하고 수업 끝나는 거. 오케이? 자,